So let me get started. And so then we're continuing our discussion of the gross Vertices equation. And today we'll actually get the equation finally after all this preliminary stuff. And so we'll discuss this equation by the end of the hour today. Okay, so you remember what it is. You remember that there are these conserved quantities. And we're interested in a regime where the total energy is of order log epsilon, which means that the modulus is very close. The modulus squared is close to 1 in L2. Okay, and so our goal is to prove a theorem about dynamics point vortices. I'll state the theorem later today. We have this first theorem about vorticity concentration. So the conclusion is that under reasonable hypotheses that will hold, in particular, when we study the gross Vertices equation, we will be able to find points C1 up to Cm such that the vorticity is very sharply concentrated around those points. And we saw that what this conclusion means is that the set where the modulus is less than a half is contained in a bunch of balls whose radii add up to order epsilon of the alpha. And then the degree, the winding number around which those balls is say d sub I, and the centers are c sub I. Okay, so and then in preparation for the next term, we stated. Okay, so again, the situation we'll study in gross Vertices is we'll look at vorticities of this form. So the vorticity will be a sum of basically, well, the ideal vorticity corresponding to point vortices would be a sum of delta functions with multiplicity pi times d sub n, where d sub n is plus or minus 1. So I didn't say this before, but we've seen that roughly speaking, the energy of a vortex of degree plus or minus 1 is pi times log 1 over epsilon plus lower terms. The energy of a vortex with a degree d in general is d squared. It scales quadratically in the degree, d squared times log 1 over epsilon times itself. And so, for example, a vortex of degree 2 is twice as costly energetically as 2 vortices of degree 1. And so in all of our arguments, we'll make very strong use of energetic considerations. And so if I have a degree 2 thing, and I can split it up into 2 vortices of degree 1 and thereby liberate a lot of energy, that's a difficult situation to analyze with the techniques we use. Okay, anyway, so we can then define, so then J star would be the, and so here, this is not gross, this is what it's the velocity field generated by those point vortices. So its curl is that measure omega, its divergence is 0, and it's tangential on the boundary. I can then define the renormalized energy by looking at the, I look at the L2 norm of this J star. I cut out balls of radius r around each vortex. As I let r go to 0, I'll find that the total energy of the L2 norm diverges, but it diverges in a way I can control. It diverges exactly like log 1 over epsilon, log 1 over r. There's log 1 over r divergence for each of the m vortices, pi log 1 over r. So if I subtract that out, I'll get a finite number. Okay, and then it turns out we can construct gross Vertices wave functions with the given vortices. And there, okay, so then in this, I'm just talking about divergence-free vector fields. Here I'm talking about gross Vertices wave functions. And so there's some kind of optimal way for the modulus to go from 1 down to 0 in a core radius epsilon, and that has a certain energy, and that gives rise to this gamma here. And so if you do this construction and you do the optimal way of you sort of optimize this profile, then you get some constant. And I won't define it, but it's sort of the optimal constant of this construction. Okay, and then if we wish, there are explicit formulas for all these things, for the J star and the W and so on, in terms of the Green's function for the Laplace norm domain, which we can write as the sum of a log and a regular part. And so I've recorded these here. Here's the Green's function. Here we write as the sum of a log, and so by definition, the other part is the regular part. It satisfies some equations, and we can express, say, the B sub R kernel, this K up here, in terms of that regular part. And similarly, the renormalized energy can be expressed in terms of those things. I don't know if we'll need these exact expressions. Okay, and so the second theorem, which we started to discuss, is here. And so remember, we're kind of entitled to assume the hypothesis because the previous theorem tells us that we can often, under reasonable assumptions, given a wave function psi, we can often find some points c. And let's see. And degrees d such that this holds. And so, right, let me always assume. So here, remember, rho sub c is, so what it says is this number rho naught is smaller than the minimum distance between any pair of vortices or the distance from any vortex to the boundary. Okay, so I have this, this sort of scale of closeness of vortices to each other to the boundary. Okay, so I'll always assume that's bounded below. Okay, and then, and so there's some error terms in this theorem, and the constant depends on things like rho naught. And I don't know, maybe the d's, d sub 1 up to d sub n. Okay, and so what the theorem says is that this construction, who I alluded to, I kind of described it in words on Monday. The construction of this psi epsilon star, if I want vortices near these points, see if I want this kind of configuration of vortices, this is really close to optimal. So anyone whose vorticity, any psi whose vorticity is also close to those things, its energy is bounded below by the energy of the explicit thing we constructed, plus some positive terms. And then there's an error term which can be negative who's tiny. Okay, and so this says that not only is this psi star close to optimal, but that it says, so it tells us that if the energy of psi is close to the energy of psi star, then psi looks a lot like psi star. Its modulus is close to 1, for example, is very close to 1. I mean, so it's, and the phase of psi, or of the gradient of the phase of psi, is close to the gradient of the phase of psi star, at least if I stay away from the vortices a little bit. Okay, so here I'm writing d of c and s is the domain with balls of radius s cut around points c sub 1 up to c sub n. Okay, and so that's the theorem, and we started proving it, and I'm going to sketch the proof very quickly. I'll sketch some ingredients in the proof, and then we'll move on to actually the gross Vertices equation. So we started, so here's the proof ingredients. So ideas. Okay, so first let's look at the hypotheses. And so our hypotheses are, among other things, that, well, the vorticity of omega is close to this given configuration. Sorry, the vorticity of psi. On the other hand, by construction, the vorticity of this psi star is also close to the given configuration. And so then by the triangle inequality, the vorticities of psi and psi star are close to each other. Okay, that's easy. Let me, okay. I've lost something. Okay, here it is. And so then, and so my goal is then to prove a lower bound for this difference, to show that this is basically positive. And I'll start as follows. I want to decompose this. So I'll decompose this into contributions away from the points C, the vortices, and contributions near the points C. And here S of epsilon is So remember the, right, so the, everything is close to each other. I should think of the, right, so the vortices of psi and psi star, for example, are close on a very small scale, epsilon the alpha. I'm looking at, so now I'm cutting out balls of a scale like epsilon to the 2/3 alpha, which is much bigger than the scale of closeness. So I have these, so they're close and on a ball which is still small, but of a vastly larger radius. And I cut out those balls. That's what I've done here for S epsilon in this range. Okay, so this is much bigger than epsilon to the alpha. And okay, and so then I have the contribution from away from the vortices and the sum of the contribution from near the vortices. Okay, and I'm basically going to say for the second part, just trust me. So I'll say a little more than that, but not much. But we can at least do the, we can see the idea of the first part. And so we can see where we use the hypotheses as sort of a satisfying argument. Okay, and so this is what I did at the end of the hour last time. There's just this pointwise identity. And so in thinking about this, one should always think of this J being density squared times the gradient of the face. And so this says, and so J of psi over psi is really rho e to the I phi. And this J of psi star is sorry, this is rho times gradient phi, and we should think as being gradient of phi star. If phi and phi star are the phases for the psi and psi star respectively. Okay, so we have this, and so, right, so my goal is to show that, so what the theorem says, in fact, is that this difference it says that this difference is bigger than the integral I have here on the right. The theorem says that E epsilon of psi minus E epsilon of psi star is bigger than this integral over a ball, okay, for S epsilon being alpha, being epsilon to the, sorry, this is a, epsilon to the alpha over 2. Okay, so the theorem says that E epsilon of psi minus E epsilon of psi star is bigger than the integral of D sub C of the domain of balls of the size epsilon of the alpha over 2 cut out of this thing. And then it says that everything else is an error term. And so our task is to show that the blue integral is small, and that these guys are small. That's what we need to do to prove the theorem. Okay, and oops, I need to shift. Let's see if we can do this by hand. And let's get some lines on the paper. I think that improves my terrible handwriting a little bit. Okay, and so our goal is to estimate this thing. And so I'll write, say 1 sub epsilon to be the characteristic function of the set D of psi S epsilon, just to save writing subscripts. Okay, and so our goal then is to estimate the integral over the domain of this thing. So here's, so this characteristic function is cutting out the balls for me. And then this J of psi star. And remember, this is something we know explicitly. This is really, right, so the point is that, and let's say, all right, J of psi star Okay, so this is this guy we know explicitly. Okay, I'm gonna first add and subtract. Okay, and so I've added and subtracted this term, just j of psi. Equals plus a2. Okay, then a1. Okay, well, that's right. TF. Okay, and then so remember this j of psi is, well, okay, so really it's modulus squared times the gradient of the phase, and so j of psi over psi is the modulus times the gradient of the phase, which is bounded by this. In other words, j of psi is the form of inner product of psi with a gradient of psi. So if I divide by the modulus, I'll get this. Okay, and then this is less than or equal to, how about, let's say, j epsilon, actually I don't need an epsilon on j. So this psi star epsilon is modified only near the balls, and so away from the balls, it's just this j star. It's the ultimate thing. Okay. L infinity, if I say away from the vortices. And then I can multiply this by, say, grad psi squared over 2 with a epsilon and 1 minus psi squared over 2 epsilon. Okay, if I want to, I can multiply this by 1 plus psi. That just makes it bigger. And 1 minus psi times 1 plus psi is 1 minus psi squared. So by replacing psi by psi squared, I just make it bigger. And then, and you see this is exactly, okay, I'll return to this in a second, but this is the epsilon times the energy. Maybe with a constant because I have a 2 here instead of 4. Okay, and this, on the other hand, it turns out, well, so what's this J look like? This J is, again, it's the velocity field generated by these vortices. We know that the velocity field, that it diverges like 1 over distance to the vortex. That's a ubiquitous feature still true in the setting. And so if I'm staying a distance s epsilon away from the vortices, then the velocity will be like 1 over s epsilon. It's like at worst epsilon to the minus 2 alpha over 3. And this is certainly this looks like epsilon to the alpha over 3 times log 1 over epsilon. Okay, so that's we don't need to worry about that. Although I may have gotten some details wrong in say when I had an alpha over 3 and I may have forgotten the logarithmic contribution. Okay, so that was the easy term. Let's look at the other term. And this is the interesting term. And so the, here it is. Let's copy it. Okay, I'm afraid I can't erase this. Okay, good. And so how do I bound this? And so the idea is this. So what I'll do is I want to write this as a curl of something. And if I can do that, then I can enumerate by parts. And exactly what I know about the closeness of psi and psi star is that their vorticities are close. And this is omega of psi minus omega of psi star. And this is small. This is like epsilon with the alpha in a certain norm, and the norm is a dual norm. The norm is this flat norm, which says, and so then, well, so then this is less than or equal to whatever I have here. It's really the I believe it's the gradient. Okay, and this is going to be whatever this is, times a constant times epsilon to the alpha. Okay. So my task is to okay, and so then it's so I get this from F estimate, and I can see how my hypothesis of the closeness of the flat of the vortices in the flat norm is useful. Exactly what it's used for. Okay, and so how do I do this then? Well, I need to figure out how to write. How do I write? So this J star as the curl of something. Well, I can't quite do this, but recall, so I'll do this with error terms. So recall, so this J star again is the velocity field generated by these vortices, and the way we find it is we take the point vortices, we invert the Laplacian to get a stream function, and then we take the curl of the stream function to get the vortices. And so we already know that this J star by construction, J star is the orthogonal gradient. I would think there's a minus sign of some psi star where okay, the boundary condition is nice because I need vanishing when I use this definition of the flat norm up here, which I did. I need test functions to vanish on the boundary, and so I have that here. And so the idea is to the idea is what? Say psi epsilon tilde, I don't know, is psi star in this domain with the balls cut out in the and say harmonic. In the balls. And so what happens? So then, and so the point is this. The point is that this will equal exactly, so on the, away from the vortices, it will equal what I want. Plus, and then there'll be contributions in the balls. Well, okay, let's write like this. There'll be some, and so these are supported in the balls, and they're small. Okay, and so the challenge then is to well, okay. First, let's look at this. Okay, so again the right. So one thing we can see is that the gradient here, the thing I'm estimating, because by construction, the gradient of size is really this J star. This again is the alpha norm J star, which is of order epsilon of the alpha. Sorry, epsilon of the minus 2/3 alpha. And so this whole thing will be epsilon of the alpha over 3. Good. And so the task is just to show that indeed to get estimates on this piece and to then verify that when you put in some error terms, that the error terms don't destroy anything. So that's the idea. And what I want to emphasize is, again, my hypothesis, which is here, how nicely the hypothesis goes with this energy decomposition. So I split the energy in this pointwise way. I have to estimate this term, and this term has the structure of being essentially once I integrate parts, it's exactly the difference of Jacobians multiplied by a test function, and that's what I can control. So so upon integration, this bad blue term becomes negligible. It's stuff we can estimate, and we're left with the good positive terms. And so for the estimate of T2, so so I'm going to totally omit this. But let's say, I mean, one thing I can do is I can average over. So the previous estimate is valid for this S epsilon in a certain range. I can average over choice of S epsilon. I can find some radius on which this quantity is very small. That would say that the phase gradient is very close to the phase gradient for the known good behavior. And so I can do that. I can then replace, I can replace psi in this ball with good control of boundary values, stuff like that. I can again appeal to this covering argument by these vortex balls and get more information from that. These are the kinds of things one does. And so it's not especially easy, but well, okay, let's only say this. So my situation is I'm estimating the energy in a bunch of balls. And I know that within each ball, psi and psi star both, they both have, so I have a ball whose scale is epsilon to alpha over 2, say, alpha over 2/3 alpha. And I know that the vorticity is concentrated in a much smaller scale, epsilon to the alpha near the center. And so the claim is that for any function psi with this property, its energy can be not much smaller than that of this psi star, this explicit construction. Again, that's not easy, but the tools are tools we've seen in action, these covering by vortex balls and the kind of stuff I've just sketched. Okay, so we'll have to leave it at that and move on to the final theorem, which is here. Right. So and let's, is this it? Yeah, that's it. Okay, and so here's the theorem I want to discuss. And this is finally a theorem about dynamics of point vortices in the gross Physiology equation. And here's what it says. So, so I'll always assume that I have a bounded, connected, simply connected domain with smooth boundary. And I want to solve the gross Physiology equation with the vorticity initially concentrated around these points. A1, 0 up to AM0, so the 0 indicates its initial data. And with these integer degrees plus or minus 1, so these are singly quantized vortices. The points are some distance away from each other. Okay, and so then I let this A be a map who, so A at every time t is a collection of m points in the domain. And so this is really the point vortex ODEs as we described above. And so the point vortex ODEs are really given they're driven by this renormalized energy that we discussed earlier. So the energy I get by cutting out balls of radius r around the vortex locations, computing the L2 norm, subtracting the divergent part, which is m pi log 1 over r, and letting r go to 0. And so this is the party energy, the finite party energy, where I don't worry about where I'm able to throw away the contribution of the rapid rotation around each vortex. Okay, and so that's really a way of writing the point vortex ODEs. I see there's a question. I hope it's a question. So are there some typos in gradient subscripts? Yeah, there could be some typos. And so what I want here is, so I want to view W as a function of A1 up to AM, and then these D's are fixed. So I'm only going to vary the A's. And so, right, so here I mean the gradient with respect to the mth copy of here, the mth variable. And this would be the same thing. So there should be a W of, here's a typo. This is an A sub n. And this H, of course, depends on the degrees D. So that's why we see a H, we see a dependence on D here, but not there, because I didn't write. Yeah, and so this grad M is the same as grad A M. Okay, so I take these points, this later, and I solve the point vortex ODEs. These are exactly the same ones that we would have for the Euler equations. And I assume that my solution has the property that the for some time interval up to time t, the intervortex distance is bounded away from 0, and the distance of vortices to the boundaries they're all bounded. They're all greater than some number rho naught, fixed positive number. Okay, so now I solve the gross Physiology equations with with Neumann boundary conditions. And here are my assumptions on the initial data. I assume that the vorticity is initially concentrating around these points up here. So I have these points who are initially for the point vortex for these ODEs. And then I assume that for the PDE, the vorticity is concentrated around these points with the right signs. And I assume, so the first assumption says, this, and the second assumption says that the energy is basically as small as possible. Given the first assumption. Okay, so I put vortices in the initial data and I assume that the energy is as small as possible given these vortices. And so what the theorem we've just finished discussing says is that under these conditions, this psi epsilon 0, at least away from the vortices, looks very, very much like the psi star, like this explicit construction with this velocity field given by essentially the velocity field that would be generated by point vortices in order. Okay, these are the assumptions. And the conclusion is that, well, then on this time interval, the vorticity at time t, the vorticity of the wave function psi at time t converges this. So here I should emphasize I'm considering a sequence of functions. And this is a statement with their behavior in the limit as epsilon goes to 0. And so the vorticity converges to point masses. The point masses are located at these points that I get by solving the point vortex ODEs. That's the conclusion. Okay, and so this is a theorem from about almost 25 years ago, late 90s, more than 20 years ago. And well, let's stop and compare it with the Euler theorems. And so the Euler theorems, here I have pretty rigid assumptions. So this is a strong assumption. So this really forces this psi epsilon 0 to be essentially a small perturbation in some sense, a vanishing perturbation of this psi epsilon star we construct explicitly, the energetically optimal wave function with vortices at the given location. And so, and this also forces the, so this is a strong assumption. Okay, anyway, so what I'll do in the remainder of today and tomorrow and Monday, I'll talk about the proof, but hopefully on Monday there'll be some time to summarize and talk about this stuff in general. And so I'll just discuss ingredients in the proof. Well, let's see. So the strategy of the proof. Well, let's look back. Let's look back at what we know. So the first thing we know is this. Which says that let's imagine for my initial data for the theorem, for my initial data, I have some condition like this satisfied, but the right hand side is tiny, is going to 0, and so we can imagine then that in fact it's a true fact about the Gross-Pettievsky equation that this psi changes is a continuous map into the Sobolev space H1. And so in other words, as time changes, the gradients evolve continuously in L2. And this is that the vorticity will evolve continuously in L1. And so this right-hand side, sorry, the left-hand side will be continuous function time. Okay, so for a while at least, if this assumption is true at time 0, it'll be true at later times. And another point to make about the theorem is that, let's go back and look at it. In the theorem, I have these assumptions on energies. And so we've seen that for the Gross-Pitaevsky equation, this energy is preserved by the evolution. So this is independent of time. And it's also true, it's easy to check that for, well, in fact, we can see right away, for this system of ODEs here, this W is preserved by the evolution, right? It's sort of obvious that, so note W of A of T, D is constant. Okay, if I carry out this differentiation, I'll get the gradient of W, the dot product with, or the gradient with the M component of W, the dot product with dAm dt, and that's manifestly zero. It's a Hamiltonian flow. Okay, so both energies are preserved by the flow, the ODE energy and the PDE energy. And so, okay, so what was I looking at? We're looking at this. And so anyway, if this is true at time zero, it'll also be true at later times. So this theorem will be available to us, and at least for short times, as long. And so among other things, this implies this is a kind of compactness result. If I have a sequence of psi epsilons with epsilon tending to zero, satisfying these assumptions, then so this then I apply the theorem to each psi epsilon. I find it's well approximated by a sum of m delta functions. And then if I look at things of this form, if I have a sequence of things of this form, these are compact in very strict norms. In fact, I can extract subsequences so that the xi, so that every xi can converts to a limit, and then and so things of this form are compact, and the omegas are getting close to those things. And so this, so right away I find that if I have a sequence satisfying these hypotheses, and as epsilon tends to zero, then they must have a limit, and the limit must be exactly a sum of delta functions of this form. Okay, so so we have compactness, and we know that any limit must be a sum of delta functions. So the first thing we'll do is, well, I want to, but so note. Theorem one implies as long as, okay. I sometimes activate Siri by mistake. You can see on my screen, stop, go away. Okay. Okay, that worked well. Okay, good. So theorem one implies that as long as omega minus we have so in other words psi epsilon, if I can find some t's for, then as long as it's true, then omega of psi epsilon at time t is precompact, so it converges to a limit. After passing subsequence, it converges to a limit of the form pi sum di delta xi I is 1, 2, n. Okay, so we have compactness, and so we'd like what I'd like to do, and so this is for any time I have compactness. What I would like is to say I can extract a subsequence so that, so I want a subsequence such that this holds for all t. Okay, and so for this it needs, for this it suffices, or for all of t in sum 0 up to t1. Right. To show that, say, what do I want? Okay, let's say this. I don't know, C t minus s as long as, or omega of psi of, well, no, okay, let's do so. Let's say. As long as the vortices remain close to their initial, as long as the vortices remain close to their initial locations, then in fact they move with a bounded velocity. So you see, if I can do this, then what this would say is that if I consider these vorticities as a map from, well, from time into what, into some space of measures, or L1 space, but I have a weak topology, and I know that in fact the image of these maps. So I have, so for each epsilon, I have this function that takes t to the vorticity of psi epsilon time t. Okay, so this is a function that takes time into the space of measures. And I know that for each t, the image is precompact in a certain topology. If I can show that these functions are equicontinuous, then essentially some variant of the Arzela-Ascoli theorem will tell me that I can extract a conversion subsequence. So so it's not bounded and equicontinuous, but it's equicontinuous and precompact for every time. So this is really Arzela-Ascoli. Okay, and so how do I do this? So what I'll do again and again, I'll do this starting next time, is I'm going to control so my goal is to control how the vortices move. And I know I have some information. Here's what it is. In particular, I have this equation for the evolution of vorticity, which will tell me that is, say, the gradient of grad perp of psi, grad psi tensor grad psi. Okay, we have this information, and so the first idea is, well, we'll do this next time, but I'll use this again and again to extract more. And so first I'm going to get crude control. I'll use this, and you see, the point is, I know quite a lot about psi because using the Theorem 2. Theorem 2 tells us where the energy of psi, the L2 normally gradient psi, is distributed. It says that if it tells us, it gives and so for example, it tells us that we know that the gradient diverges like log epsilon, but we also know the divergent part is concentrated around the vortices. That's one thing that Theorem 2 tells us. And so away from the vortices, the energy is uniformly bounded. If I'm a distance away from the vortices, the energy is like, if a distance r away from the vortices, the energy scales like 1 over r maybe. So and so the task is to control. I'd like to use this to control, and so this, on the other hand, is like a sum of phi at some points a I. This is what I'd like to imagine. So once I can prove convergence, or let's call them bi of t. Once I can prove compactness, then I'll know that this is true. And so this formally is the sum of the gradient of phi at these points times d bi dt. This is giving me information about the. So again, formally, this is telling me how the vortices are moving. Okay, and so then what we'll do is we'll use these identities again and again to, we'll sort of, essentially we'll use this several times to get more and more information about the vortex velocities. First to past limits, then having past limits, we'll look at things more carefully. We've already done everything we will with the first equation, so all we care about that is that the energy is conserved. And the second equation is going to intervene in a crucial way, as we will see tomorrow, I believe, or maybe next month. Okay, that's it for today. Let me stop here.